Welcome. In this video, we are going to learn about the different metrics that we have for regression. Evaluation metrics are very important to evaluate how good your model is. Evaluation metrics are used to measure the quality of your statistic or machine learning model. It tells us how much of a good model you have created. Okay, so there are various evaluation metrics for different kind of problems. For it is very important to use multiple evaluation metrics to evaluate our model. It will tell us how good our model is and how good it is to predict out data. This is because a model may perform very well using one measurement from one evaluation metric. What I mean by this is we should not only predict by maybe one evaluation metric, but we should be using a couple of them. Why? It's because one metric might work better than the other one, so we need an mean of them. So one measurement from one evaluation metric but perform poorly using another measurement from another evaluation metric. What I mean by this, maybe MSE works better on my model, but RMSE does not works better on my model. So you should be always having different kind of evaluation metrics for that. Using evaluation metrics are critical in ensuring that your model is operating correctly and optimally. Now, for regression, we have particularly three kinds of metrics which are used a lot. We have bunch of more, but these are something which we mostly use in our day-to-day life. Looking into the different kind of evaluation metrics, one thing that you should be noting out is we don't use accuracy we don't use accuracy for regression. This is something that a beginner actually makes a lot of mistake. They usually find that we should be getting out our accuracy in regression. It is 80% accurate or it is 90% accurate. But let me give you an example that what we predict is continuous data, and predicting continuous data exactly as it is not quite possible. So let's say a height of a building, we are creating a model where we have to predict the height of a model. So this is a model and this is somewhere 13.65 and our model is able to predict 13.2. Now these two are not common, right? Both of them are just a different thing. 13.65 is not equal to 13.2, so we are not able to predict the same thing, but we can see that we are predicting somewhere nearby this. So we need some different metrics for this. That's why we have MSE, RMSE and MAE. So let's start with mean square error. So in mean square error, it is a very important loss function for algorithm fit or optimized using the least square framing of a regression problem. Here, least square refers to minimizing the mean square error between the prediction and the expected value. Now, let me just shorten it up for you. Y cap, we know that this is our actual value. Uh, so Y is an actual value and Y cap is an predicted value. So just as we could see in the cost function where we had to reduce it out, the less the value of this, so the much the lower the value of this will be, the better our model will be. So there's not much of a difference. So let's say the actual value is somewhere between 2.2 and our model is able to predict 1.1 or 2.1 exactly. So the difference is 0.1. So that is really less. The less the amount of this will be, the better our model would be. Now here yi, what we can see is the actual value, is the ith expected value in the data set, and y hat I, that is this one, is the ith predicted value. The difference between these two values is squared, which has the effect of removing the sign positive in a positive error value. What I mean by this is we have already seen the difference between 2.2 minus 2.1, which is again zero point 0.1, right? But let's say we have quite just the opposite thing. So the actual value is 2.1 and our model is predicting 2.2. So the difference comes around zero point 0.1 minus zero point 0.1. So for this negative sign to get positive, we have put out a square value. That is where we have this square notion over here. And then we are doing the same thing for each and every value in the data set. So this is our data set where we, let's say we have 2.2, 2.2, 2.1, then 2.1, 2.2. Similarly, we have 3.1. For that, we have, this is y and this is y hat. Okay. And for 3.1, we have 3.2. Let's remove all of these. Okay. And let's say 4.5, 3.9. So for this, the difference will be somewhere yi minus y hat is 0.1. Then again, we have minus 0.1. Then again, we have the difference of minus 0.1. And then 4.5 to 3.9, it's 0.6, sorry, positive 0.6. Now what we are going to do is we are going to sum all of these up. As you can see, n is the total number of values that we have, total number of rows that we have, number of rows. Okay, that is the number of items, number of rows, and this is divided by that. So we are getting somewhere between, let's cancel this, and we are getting 0.5 by n is our 5, so we will be getting a value of 0.1. So our MSC is equal to 0.1, which is again a very good value. The nearest, the best MSC value should be 0. Okay, so if the value is 0, then it means that all the rows that we have predicted is exactly what we have in the expected value. So one is 1 point, like 2.2 will be predicted 2.2, 1.2 will be predicted 1.2, which is again not quite possible. So anything that is nearby 0 is a good fit. So that's about mean square error. Then we have root mean square error. It's quite the same thing, but what we have done over here is we have square root MSC. So the difference over here just comes over here. You have square root MSC. Now, what exactly is the reason for this? The reason is quite simple. So over here, the values just change out. Let's take a quick example of this. Let's say for MSC, if we are calculate MSC, you can look over here. If we are calculating MSC, so we have a square sign over here. So we are trying to predict, let's say rupees, how many rupees we are predicting how much rupees something might be. So the last answer that we will be getting will be rupees square. Now to remove this square, okay, you can just do MSC also, or to remove the square, we can just use RMSC. That would be root of MSC, which will just give me, let's take R square. So it will just give me exact rupees. That is the exact unit that I was looking for. That is the original unit. So you may recall the square root is the inverse of the square operation. MSC uses the square operation, and that helps us just remove the sign. So that's basically root mean square. The last thing that we have is the mean absolute error. This is another popular metric because like RMSC, the units of error score match the unit of target value. What I mean by this, like similarly in RMSC we had rupees, so rupees is rupees only. Rupees will be equal to rupees only, but in MSC again it will just convert it to the square value of it. Now what we have over here is we have the absolute value over here. So as the name suggests, ME is the score is calculated as the average of the absolute error values. So this error values, y is the actual output value, y cap is the predicted output value, and what we have over here is the abs function. Abs function. Rather having a square notion over here, what we are having is the abs function. So we don't need to square out the values to just remove the negative sign. We are just putting an abs function. Okay. that is the absolute function, and it will just convert the negative to positive, and positive will be just remain positive. Now what's the importance of this is whatever value that you will be getting over here will be very less. So for RMSC or MSC, what we were doing was we were squaring out the values. So if we had 5 rupees or 0.5 or somewhere between 4.5 the value was, in MAE it will be very less, nearby 1.3 or something, just the half of it somewhere. Okay, not exactly the half, but somewhere very less than that, because we are not just gradually increase the power of it. Okay, so that's what this does. So this is due to, as in MSC and RMSC punishes large square errors more than smaller errors, inflating or magnifying the mean error. So this is due to the square of the error value, as I told you. The MAE does not give more or less weight to different types of error. Instead, the scores increases linearly with increase in error. That's about it. These are the three things. Let's jump into Jupyter Notebook and look in our previous data set of univariate linear regression of what exactly these are and how to get it in sklearn from sklearn library. We are back in our video. Let's import the matrix. So from sklearn import matrix. Let's run this to get out all the matrix that we need. And rather than writing everything, let's paste out a code over here. So we don't really need to write any formula in the backend. So whatever we had was a very intuition level talking in the lecture video, but over here we will just execute, we will just learn it from a very applied manner in the practical session. Okay. So intuition is something which you need to understand the backend of the algorithms, and applied manner is something which you need to get the practical aspect of the industry aspect where to use it out. So as for the applied manners, so for the calling this out, we have matrix dot mean absolute error, that is the MAE, y test and y pred. So what is y test? It's the expected value, and y pred is the predicted value. So same thing for mean absolute error, and same thing for mean square error. So we can see that MAE, as I said, that it will be very less or quite less than MSC and RMSC, because we have the absolute, okay, error. MSC again is 1.38, which is quite okay, and RMSC is 1.17 again, which is quite okay over here. As we are squaring out the value, so RMSC is lesser than MSC. Okay, square rooting it out. So RMSC is quite less than MSC, and MA is the smallest because we are not doing anything. We are just absoluting the values. So we are getting the least value. So these are the three evaluation matrix that we have for regression. So that's it for univariate linear regression. In our next video, we are going to start with multivariate linear regression. Thank you.